Welcome to the Rob Seco Field Ready Podcast with your host, Jim Robinson.
Hello and welcome back to the Rob Seco Field Ready Podcast. I'm your host, Jim Robinson. Well, the birds and the bees of row cropping is a critically important topic and time of year. In many geographies, corn pollination is underway or already complete, and seed pollination is rapidly nearing completion. But we're going to take a look at why this process is so tricky and important, and also why are sterile plants so good for your seed. Joining us today to talk about that, we have Aaron Wulf, Rob Seco's production manager. Welcome, Aaron.
Hi, Jim.
Well, Aaron, welcome back to the podcast, and I'm going to start off with just a quick question of, can you break down for us a high-level overview of pollination during seed production?
Certainly. When we think about seed production, we're looking for using inbreds for pollination and for the female characteristics or the seed characteristics of that female inbred, and then the pollen from the male.
Now, what makes an inbred a male or a female in seed production?
We'll look at different characterization aspects, whether it be yield, seed size on the female portion, and pollen on the male side.
Yeah, so an inbred that makes a lot of pollen and releases that pollen over a long duration is more likely to be used as a male, whereas an inbred that puts on a really nice ear with nicely shaped kernels that can be used for seed would be on the female side.
That is correct, yes.
Perfect. So how does this look in a field? I'm sure plenty of people have driven by seed production fields. Some may look goofy, some you may not even recognize from the beginning.
That is true. In some cases, you may not recognize a seed field from a normal commercial field until pollination. At that time, you'll start to determine the difference between a male and a female, which we'll talk about a little bit more later. But a typical row pattern for a seed production field is 4 rows of female and 1 row of male.
Mm-hmm. Yep, that way those 4 rows of female can maximize the number of ears harvested and thus the amount of seed produced on the field.
That is correct.
Perfect. So as those female rows start to get closer and closer to tasseling, what happens and what do you do to manage any selfing or pollination of the female by the female?
Sure. It is one of the critical steps to creating pure seed and hybrid seed. But the first step you'll see is the female rows being cut. They'll go through with a regular mower blade for each row and cut the tops of the about the first third, maybe half at the most of the tassel. After that, they'll wait a couple days, let that tassel extend to where they'll bring in a wheel puller. Has tire wheels that will grip together and pull the tassel out, and looking for a good removal, a majority of the removal of the field of those tassels, and then follow it up with crews going through to hand pull the remaining amount.
Perfect. So those detasselers, do they go through one time, or how does that often look?
It is very rare that you will get a crew to go through one time and clean up the field. As we all know that there's late emerging plants, no matter what field you're in. And in this case, 2 passes minimum, and could be 3, sometimes 4, depending on the particular field.
So that's a tremendous amount of work. You have a cutter coming through, you have a wheel puller, then you have anywhere from 1 to 4 different passes by detasselers to remove those tassels. Why are all of the passes through the field necessary, and why is it so important to remove every single one of the female tassels?
In one word, purity. We're looking for a pure hybrid crop. And in order to get that, we don't want the female pollen pollinating the silks on that ear. We want the male pollen only to pollinate that female to create a pure hybrid seed crop.
Absolutely, yeah. Anytime that female pollen falls onto the silk of a receptive silk of the female ear, that creates a self or an inbred. And those inbreds, when you plant them into a production field, so a farmer's field, will grow, and they're often smaller than the hybrid plants around them. They become a weed, they don't put on an ear of their own, and they suck up resources away from those hybrid plants, and therefore every percent of inbreds you have in the field is almost a percent loss of total yield.
That is correct, Jim.
So tell me a little bit more about pollination and things, because there is an alternative to doing all this pulling and detasseling and everything of that sort. Can you tell me a little bit about male sterility and why it can be beneficial to seed production?
Yes, male sterility is a concept developed back in the 60s and 70s that incorporates that sterility into the male or into the female plant, but on the tassel side to stop that tassel from extruding pollen.
And male sterility is actually a condition that can be found in numerous different plants in nature. I mean, there have been identified at least 140 different species of plants that have some form of male sterility as either inherent to that species themselves or due to intra-species crosses or just something that is a mutation.
That is correct. Yeah, there's several areas where you can find that sterility. In corn, we use a cytoplasmic male sterile to that breeders use to incorporate that sterility into the plant.
And it's worth noting that cytoplasmic male sterility differs from genic male sterility in that it's the cytoplasm, not the genome in the nucleus, that actually confers the sterility, which is actually important because cytoplasm is passed on by the mother, not by the father, and so you can do some fun tricks that way.
Yes, you can.
So what happens once you have cytoplasmic male sterility incorporated on the female side of the inbred used in a production field?
Well, the first thing you can realize is minimizing your workload in the field. You won't have to cut, wheel pull, and send crews through. What you typically do in that case is you monitor that sterile plant to make sure that there is no pollen release or future pollen release. And in most cases, at most, you might run a cutter through there once or twice at the very most.
Yeah, a lot of today's sterility methods are extremely reliable. It still does allow somewhere around 3 in every 10,000 pollen grains to be released and be fertile enough to be able to pollinate. And so doing those cuttings can minimize that and make that a fraction of a million or something to that effect.
Correct.
So this can absolutely reduce the amount of inbred seed that goes into a hybrid seed bag. But if it's cytoplasmic male sterility and the cytoplasm is inherited by the female, that hybrid seed will be sterile on its own. How do you get around that?
To work around that on the commercial side, we would blend that with fertile acres as well. That could be done at several different times. At harvest, when you harvest the field itself, you can blend as you go. Or you can blend at the time of conditioning when you clean, size, treat, and bag the product.
Perfect. That way the farmer's field has enough viable pollen to pollinate the whole field and give you the yield that you're actually looking for to create grain.
Yes.
So it's great that you can reduce overall costs and labor required for seed production by using cytoplasmic male sterility. But ultimately, why is this a good thing for a farmer?
Well, one of the key aspects to it is we can use that as a way to increase yield on their side. With that sterility in there, we can optimize the plant characterization, optimize the yield, and improve their performance coming off the commercial side.
Yeah, so not only are there fewer inbred seeds contaminating the hybrid, which for every percent of inbreds contaminating the hybrid seed, that's basically a 1% reduction in overall yield. But there's also an effect of where the pollen that's being created off of these plants actually is taking up energy by the plant to create that pollen to do pollinating. So if you don't have to make that pollen, the plant can then use that energy to stick into the ear, increase yields, and improve overall yield.
Yeah, that is correct. And in some cases, you see an increase in from anywhere from 1% to 2% with this particular model of production.
Absolutely. And, on 200 bushel corn, you're looking at 2 to 4 bushels an acre, which may not sound like a lot, but, as you're looking at generating however many bushels on a fixed acre, 2 to 4%, or 1 to 2%, 2 to 4 bushels, actually does become an awful lot of extra grain. Now, this is kind of a fun little scientific thought because a lot of people have approached this different ways to maximize the effect of using steriles in fields. There have been a number of people who have tried to improve the performance of their new launches of hybrids using sterile seed and not blending it in order to get other hybrids to pollinate that seed going through so that your hybrids look better in strip trials. That's rare, but it has happened before. But also, some of the more clever uses of this have been strategies where seedsmen have looked into using cytoplasmic male sterility to induce a xenia effect. So, Aaron, I'm not sure if you remember what xenia is.
It's been a while, Jim.
So, a xenia effect would be the same thing as getting hybrid vigor out of the kernels as you would out of a plant. So when you cross two inbreds together, you get a bigger plant. Well, if you pollinate an ear with a different genetic background, then you can actually get bigger, deeper kernels. And so one strategy that's been explored has been to use a field of sterile seed, a sterile to hybrid seed, and then plant intermittent rows of some completely different genetic background to maximize the amount of xenia you get in order to increase yield overall. It's been difficult to get that to work from a commercial perspective, but it is a fun idea overall.
Yeah.
So, Aaron, there was a big issue with cytoplasmic male sterility back in the 1969, 1970 growing seasons. Can you tell us a little bit about that?
Yeah, when they first introduced steriles and the CMS into production, it became reliable and well characterized. But what it did is it opened us up to exposure and susceptibility to the southern corn leaf blight.
Mm-hmm. And at that time, cytoplasmic male sterility, particularly the CMST, so Texas cytoplasm, accounted for almost 85% of all seed planted in the South and in the Corn Belt.
That is correct.
Mm-hmm.
Yeah, it was a very large exposure to the industry, something that wasn't foreseen until it was a little bit too late.
Mm-hmm. Yeah, so there were epidemic proportions of southern corn leaf blight that were introduced that year, and those 2 years, absolutely devastated yields, and also caught the seed industry a little bit flat-footed because, as you can imagine, you have to start parent seed production several years before you actually produce the hybrid that's going to go on a farmer's farm. So it takes a couple of years to actually adjust to these things.
Yes.
Mm-hmm.
Yeah, it does.
Now, an interesting little tidbit to this is in 1969 and 1970, there were those massive outbreaks of southern corn leaf blight. Farmers were furious, as you can imagine, and looking for any alternative that they could to Texas cytoplasm. And that also happened to coincide with the very, very early days in the identification of a hybrid known as B73 by Missouri 17. And so if it weren't for the T cytoplasm and southern corn leaf blight, we actually probably would have seen a longer duration of time until B73 Missouri 17 became a really big hybrid in the industry. I think by 1973, B73 by Missouri 17 was almost 6 million units of corn across the United States. And it can largely thank T cytoplasm for that.
Yes, we can.
B73 wasn't ultimately converted to T cytoplasm, but later converted to one of the several of the other male sterile versions.
Very true.
Now, tell us a little bit about today's male sterile versions. Are they still susceptible?
No, they're not. They've identified where that susceptibility has come from, and the sterility and the biotech around it are not associated with those diseases. Mm-hmm. And they have developed that sterility to work through the that outbreak and the issues that we caused back in the 70s.
Absolutely. And interestingly, that original T cytoplasm was actually functionally the same mutation that made the T cytoplasm male sterile, was the exact same mutation that made those plants more permeable to the southern corn leaf blight fungus actually get into the plant and ultimately the mitochondria itself. So, functionally, you couldn't separate the two. That's why these new versions were so much better in creating sterility and then not adding additional fungal susceptibility. So, Aaron, just to summarize overall, right now we are pollinating corn across much of the Corn Belt. Actually, by the time this episode is released, the majority of seed production will have pollinated, although there still will be pollinating in seed fields going on until the first 1 or 2 weeks of August or so, typically. And the male and female rows, the male rows being the ones where the tassels are left intact to shed pollen onto the female rows that are detasseled, those are going to be, in a lot of cases, detasseled, pulled, etc. But you will see some seed fields where you may see 4 rows of female plants and 1 row of a male plant on down the field where the females aren't necessarily cut or detasseled to the same degree as you see in the other fields. This is usually because there's some sort of form of male sterility going on, the majority of which comes from a cytoplasmic male sterility that can minimize the amount of inbreds that occur in the field due to reduced female selfing, and can actually increase hybrid yield through the reduction in the amount of energy required to produce pollen, thus shifting that energy into the ear. And today's male steriles tend to be a lot more reliable than those of the 1950s and 60s, being T cytoplasm, which increased susceptibility to southern corn leaf blight and caused a massive issue within the industry that's now luckily over and fixed. So anything you'd like to add on sterility and seed production?
No, I don't think so, Jim. I think we covered most of it for today.
Excellent. Well, Aaron, thank you so much for joining us again.
Thank you.
As always, be sure to tune in on the 1st and 15th of every month for new episodes. Until then, stay field ready.
Thanks for tuning in to this episode of the Rob Seco Field Ready Podcast. Join us next time to be field ready.
A Hurrdat Media Production.